Great. So thank you for the invitation to give a talk about YAMTL. So I'm going to show how to use YAMTL, a new model transformation language, for defining model transformations that can be used from within your own code in Java in this case. First, I'm going to talk about a few MD use cases in which model transformations are relevant for those of you who are not that familiar with model transformations, although in this context, I would assume that everyone knows what a model transformation is. So model transformations play a relevant role for transforming models. For example, we can have models that are used for capturing the relevant conceptual aspects of a system, and then we can transform that model blueprint into actual code by applying a sequence of model transformations and model-to-text transformations. And it will be a forward engineering process. We can also use model transformations for implementing reverse engineering processes. First, we would work with a model-based parser that would extract data from a program, and then using a sequence of model transformations, we could analyze that data in order to refine or provide more abstract models that can be used for transforming, for extracting relevant data, or for actually starting a rejuvenation process of an existing legacy system. Model transformations also play a relevant role for implementing consistency maintainers. And when we are using different modeling languages for modeling a system, for example, we could have a component diagram for capturing the architectural structure of a system, and we could use class diagrams for capturing the internal design of each component. So whenever there is a change in one of those models, we need to check that the related models are kept consistent. So, for example, we need to check that the internal implementation of the interfaces of the component diagrams are correct within the class diagram. Once we start changing different views of a system model, we may break those consistency relations, and we can use model transformation in order to define the consistency relation and to check that they are correct, and also to repair them in case there is a change that breaks the consistency relation. This would be an example of a horizontal consistency relation. But consistency relations also apply in a vertical way. So if we generate code from a blueprint, as I was explaining earlier, we introduce a change in the component diagram, we may want to reflect that change in the code that has been generated. And this consistency can also be enforced using model transformations. YAMTL is the acronym of yet another model transformation language that provides a number of MDE concepts atop mainstream programming languages, mainly JVM programming languages. And in particular, YAMTL provides model-based pattern matching, model-to-model transformation, and model-to-text transformation by relying on extend. And it provides a implicit and explicit support for traceability, so that all the transformations, all the applications of transformation rules are tracked, and we can exploit those traceability links in order to execute a model transformation incrementally later on. YAMTL is provided as an internal DSL of extend, which is a Java language. And it provides very good, thanks to this integration with extend, it provides very good interoperability with the different Java libraries. What is novel about YAMTL? Why yet another model transformation language? As an internal DSL of extend, we can use any library, any Java dependency that already implements data transformations for building more complex model transformations in YAMTL. And any model transformation built with or developed within YAMTL can be exported as a dependency that can be used within any other JVM program, which is quite useful. I will show later on how to execute a model transformation, and you'll see that the integration is straightforward. By using extend, we are reusing a high-level API to work with collections, with Java collections. And we are also using the extend dialect for writing lambda expressions. And this means that we can build OCL-like queries using extend using succinct code. And the most important aspect of having YAMTL as an internal DSL of extend is that we can reuse IDE support and productivity tools. So these are, for example, the type checker, debugger, but also Java code analysis tools. And that's an important aspect because we can reuse many tools, third-party tools, for analyzing model transformation code that we don't need to maintain. YAMTL is a Java dependency that is independent of Eclipse, although it is based on the Eclipse modeling framework. So the models that we can manipulate need to be specified using an EMF meta model. Another novel advantage of YAMTL is that the model transformation abstractions are provided within the Java JVM family of languages, providing new concepts that are not available in them yet. So, for example, the pattern matching that can be implemented with Java is much more simplistic than what we can support with YAMTL. By using EMF, we can support interoperability among modeling tools. This is not particularly new, but another key advantage is that YAMTL provides high performance when comparing it with state-of-the-art model transformation languages of the same type of expressiveness. And here we have worked during the past 3 years using a number of benchmarks. We have participated in contests, and we have worked with international colleagues, and all of the experiments reassure that the performance of model transformations running YAMTL are quite highly performant. I will mention very briefly the results of a benchmark at the end. I'm going to use this example of transformation from class diagrams to relational schemas for illustrating how to use the language for defining model transformations. In this case, we have that in class diagrams, we can have classes that contain attributes. Attributes point to classifiers that can be data types of all classes. So the notion of attribute and reference are aggregated within the same concept. And for specifying relational schemas, we can have databases that contain tables. Tables contain columns, and there is a key, a primary key, and foreign key columns are identified by using a naming convention. The columns have a basic data type. Okay. So for declaring a model transformation, we simply need to define a Java class that extends the YAMTL module. This is this class provides the facade interface of the tool, providing the main API for loading models, executing transformations, and for profiling transformations. In the constructor, we need to specify the signature of the transformation, indicating what are the input models, and this is the name for the input model, and this is the package of the EMF meta model. And we have to specify what are the output models. In this case, we also have to specify the name and the package of the output meta model. In this case, we have an outplace model transformation where we get a class diagram as input and we output a relational schema. We can also use in-out domains, in-out models for implementing in-place model transformations, although this is an experimental feature at the moment. Within the constructor, we can specify a rule store, indicate where we will declare rules, and also manage helpers. And within that class, we can also use any native extend code for implementing any additional code that may be used in our model transformation. And this may involve other methods, implementing queries, or it could be declarations of data structures that we use as auxiliary data structures. For declaring, this is an example of a YAMTL transformation rule. In this case, we are transforming an attribute into a column. Rules have two main parts, which are, well, three main parts: the name, the input pattern and the output pattern. In the input pattern, we can have several input elements. In this case, we only have one. For the input element, we specify the name of the input element and the type of the element, specifying the type of the object that has to be matched here. We can specify local filters that indicate a condition that needs to be satisfied that the object that is matched by this input element. In this case, we are using an extend expression indicating that the type of the attribute that is matched, this attribute variable refers must coincide in name with the name of the attribute that has been used for declaring the input element. And we're indicating that the type of the attribute is instance of the data type. For the output pattern, we are indicating the name of the output element, the type of the object that will be created, and an action in extend that is an extend expression that will initialize the features of the objects that are created. In this case, we are creating a column, and we are initializing the name of the column with the name of the attribute that corresponds to the matched object. There are different types of rules that we can implement in YAMTL. We have matched rules like this one. Matched rules are scheduled by the engine itself, so we don't have to provide the match for applying such rules. The engine will compute the matches at the start of the transformation execution. We can have lazy and unique lazy rules that are rules that are applied on demand explicitly. For those, we have to provide a match, and then we have to invoke the transformation. I will show an example of how to do that later on. We can also specify transient rules that are used for performing some auxiliary computation, but any objects that are created with those rules are ignored and are not persisted. And we can also have query-only transformation rules in which we only have an input pattern. And those rules are quite useful for implementing queries for model validation, for example. For specifying an input pattern, we can use we can have different input elements in the input pattern, and we can use a matched object of an input element in the filter of a different input element. And this will only be evaluated correctly if there is a constraint that guarantees the control flow in which the different input elements need to be evaluated. And this is achieved with expressions. Each input element can have a filter condition, and those filter conditions are used for specifying local constraints. We can also have a global constraint that needs to be satisfied by the full match, and we can specify additional objects in the input pattern that are not matched but are derived from objects that are matched. And this is quite handy in order to simplify the matching process. When we are specifying output patterns, we can also specify different output elements. So we can create different objects in the output model. And we can use using variables for declaring local variables that are shared among all of the different output variables, so that these are only initialized ones. And we can also use end with expressions that are executed at the end of the rule. So here you see the main rules used in this transformation. We have a class to table transformation that obtains a table from a class. Then it initializes the name of the table with the name of the class. And it also creates a primary key column and initializes the name of the column with the name of the class. This reference, this new object, is used here. So let me use the laser. So this primary key column is used in the this output pattern in order to initialize the it's added to the columns of the table. And then we have the attribute to column rule that has been explained in the previous slide, and we have a unique lazy rule that creates a column from an attribute. In this case, it will be a referent. So in this case, the foreign key column is simply a column whose name has, as naming convention, the direction in which the foreign key is declared. Now, in order to see how to use, in order to see how to resolve objects, that are declared among different rule applications, we have to use the fetch operator, which plays a key role in our language. And fetch allows us to take an input object or a list of input objects and resolve them to the corresponding output objects as generated by transformation rules. If the transformation rules that have been applied are matched, the fetch object will find those objects automatically and allocate them to the corresponding, well, and it will basically, so this fetch expression will return all of the columns related to the attributes that are assigned here. And the list of columns will be assigned to the columns of the table that has been generated. When we're using unique lazy rules as the reference to foreign key column, we have to provide the match. The match in this case is simply the attribute. In this case, we're using an extend helper for identifying all of those attributes that are references that point to the class. And then with fetch, we're indicating that we want to obtain the columns that result from applying the transformation rule reference to for fk column. In this case, we have to name explicitly the name of the rule that we want to apply because it's a lazy rule. When using matched rules, we have a correctness criteria, a correctness check that is implicitly taken into account by the engine when applying transformation rules. And in this correctness check, matches need to be unique so that transformations are ensured to be deterministic. As I said earlier, we have helpers. Those can be managed helpers. We can declare static attributes, as in this case, we provide a name, and then we specify an extend expression, like in an OCL expression, defining a query for finding the data type that is a string. And we can also use queries as managed helpers implemented in extend methods. YAMTL provides the all instances operator that corresponds to the OCL operator all instances. And the main difference between managed helpers and unmanaged helpers is that managed helpers are memoized internally by YAMTL so that they are only computed once. In YAMTL, I don't have time to go through all of the features of YAMTL, but YAMTL also provides support for multiple rule inheritance and for abstract rules, which is quite handy for minimizing the duplication of code when defining model transformations, when dealing with metamodels that have inheritance hierarchies. And it also offers mechanisms for composing model transformations. And this is mainly the main composition mechanism is by using class extension. This implicitly inherits all of the transformation rules defined in the superclass, and unless the rules that are defined in a child model transformation is compatible with the signature of a transformation rule in the parent transformation, in which case the transformation rule would be redefined. And of course, we can import a transformation as a Java class and instantiate it and use it. So here we have an example of how to instantiate the class diagram to database transformation. We would instantiate the class that implements the transformation. Then we load the input models by providing a map that maps the name of the model to the corresponding path. This name must correspond to the name of the model used in the header, in the signature of the transformation. Then we use the method execute that would transform the model, and then we would simply save the corresponding output models of interest. And let's just briefly mention how to deal with incremental execution of model transformations. We can the model transformation that we have seen can be regarded as a consistency maintainer between class diagrams and relational schemas. And if we apply a change to the input class diagram, for example, we change the name of a class. So we change the name of a class. we would like to transform the class diagram, but we would only like to propagate the change that has been performed in the input model, so that only the changes that correspond to that input change are reflected in the output model. This corresponds to an output change that is defined in EMF in our tool, in the EMF change model. And this scenario is supported in YAMTL as well. So in order to execute a model transformation in incremental mode, we have the same code as before, but now we have to indicate that we want to execute the transformation in incremental mode. And we have two types of changes. We can use offline changes that are change model, change descriptions that have been persisted in XMI using the EMF change model. And in here, we would need to load the delta by indicating to which model the delta will be applied, the name of the delta that we want to, the label that we want to attach to this particular delta and the path. And then we would apply the delta to the input model, and we would propagate the output delta to the output model. And this is how it would be done in YAMTL. And finally, we would save the model, and this model would have the change implemented. Note here that there is an initial step where we execute the transformation in batch, in full, and then we only propagate changes incrementally here. And we can also deal with on-the-fly changes. So, for example, we can prepare a particular model for listening for changes, and that's done with the adapt input model method. Then we can obtain the resource or the model that contains the object that we want to modify. We would use an OCL-like query for getting the reference to the object that we want to modify, in this case a class, and we would change the invoice name. And finally, we would simply apply the method propagate delta without applying the input delta, because it has already been applied, and YAMTL would detect where the changes have been applied in the input model, and it would compute the output delta that is, and it would propagate it. And briefly mentioning,
to wrap it up in the near future.
Yes.
Great. Okay. Thank you.
Okay. Thank you. This is the last slide, almost. So this is a brief mention to the benchmark that we have used among others. In this benchmark, we have been dealing with very large models with instances of 10 million objects and almost 30 million references. In this is a well-established benchmark that many state-of-the-art tools are using for measuring the performance of model transformations. And in this case, we compare our the model transformation implemented in YAMTL against the best performing state-of-the-art tools in that benchmark, and YAMTL in batch mode. So when we transform the input models in full, is the fastest of them all. When propagating changes, taking into account that we are dealing with sparse changes and there are several scenarios, our tool is also able to propagate changes in real time. This is our tool. There were different scenarios, and our tool was slightly worse than the explicit transformation than this one in other scenarios, but still we are very, very happy with the results, because we are comparing the new YAMTL tool with well-established transformation tools. So in summary, YAMTL brings declarative model-to-model transformations to the Java world, providing advanced model transformation constructs that can be used from within your own code in Java, and allows you to reuse Java code that may already be transforming data. So you can reuse that logic. You don't have to throw it away. And it provides very good performance. And that has been shown in a number of benchmarks. And here you have a list of references in which those benchmarks are explained in detail. And this is the URL where you can find and download the tool as a Java dependency. Thank you.